All right, this is Mr. Wyrick. I'm going to do my best to kind of walk through today's notes. I got my laptop down here, so I'll be looking down at that and kind of referring back to you. So we're looking at angle measures of polygons. The first slide that we're looking at here just kind of defines polygons for us. The polygons are the ones over here in the orange. They are all connected by straight line segments. Now you can see a couple of these are kind of weird looking. There's one that looks like the L block kind of in Tetris. There's a hexagon, there's a square, there's a triangle. They're all connected by straight lines is the key thing. For the not polygons, a circle, an oval, a moon shape, a semicircle, anything that has a curve to it is not going to work as far as a polygon. On the types of polygons, I feel like these are a little out of order, but I didn't exactly type up the notes for it. We have the convex polygon that I want to talk about first. All the interior angles of it are going to be smaller than 180 because this is the one that we're going to be dealing with the most, if you want to kind of highlight that. The concave polygon is like when you used to draw little stars on your notebook or something like that. If you have, instead of all of our vertices pointing outward, you have one that kind of points back inward. That makes what they call a concavity when you get further into mathematics. And it's going to be an angle that's greater than 180. We're not really going to use those because it's going to throw off the calculations that we have. And then a regular polygon is a special kind of convex polygon where all the interior angles are congruent. They're all the same and all the sides are congruent. So our equilateral, equiangular triangle, our square, anything bigger than 3 or 4 sides instead of being an equilateral triangle or a square is going to be just a regular and then whatever shape it is. So a regular pentagon, a regular hexagon, something like that. On our next slide, we have the polygon interior angle sum theorem. It's kind of a mouthful there. It says that the sum of the interior angle measures of an n-sided convex polygon is equal to 180 times n minus 2. That sounds really complicated, but here's how it goes. You take the number of sides, you subtract 2, and you multiply that by 180. That tells you all of the interior angles added together. So for our most basic shape, the triangle, we have 3 sides. We take away 2, that gives us 1. We multiply that by 180, it's 180. So all the angles of a triangle add up to 180. We talked about quadrilaterals, parallelograms. 4 sides minus 2 gives us 2 times 180 is 360. So they all add up to 360. For the shapes we have listed here, you apply the formula the same way. So for the pentagon, it's going to be 540 degrees total on the interior. For the hexagon, it's going to be 720 degrees on the interior. And for the decagon, that last one, 10-sided, sorry, it's not more regular. I just wanted more sides to it, but you to be able to see exactly how many there were. That's 1,440 degrees on the interior. For the next one, it has the regular polygon measures. So we're doing the same thing here. We're taking the number of sides, we're subtracting 2 from that, we're multiplying it by 180. That gives us the total number of degrees in that figure. And then we are also dividing by n, the number of sides, again, to tell us how big each angle is going to be. So you can see, again, the triangle is 180. There's 3 angles. That takes it down to 60 for each angle. The quadrilateral, the square, it has 4 sides. So we take the 360 degrees. We divide it by 4, each angle is 90. And you can see some of the other ones real quick. The pentagon, 108, the hexagon, 120, the nonagon, 140, and the decagon, we decided that had 1,440 degrees. We divide that by 10, it comes up to 144. This is a nice little reference page for you. On the polygon exterior angle sum theorem, it's a big mouthful to sum up one really easy statement. If you add together all the exterior angles, you're going to get 360 degrees as long as it's a convex polygon. Doesn't have to be regular. If it is regular, then each one of those exterior angles is also going to be the same. Okay, so all of these 1 through 5 are going to add up to 360. So on our examples, the first one, find the measure of angle A. So on 17, I'm just going to type this in real quick on Desmos. I've got 360 degrees because it is, this is a quadrilateral. It has 4 sides. I'm going to subtract 101, and then I'm going to subtract 92, and then I'm going to subtract 68. And what I have left is 99 degrees for angle A. On number 18, as it's shown there, we have a hexagon that's 720 degrees. And we are going to subtract 100, 135, 110, 149, and 91. And we're still going to have a pretty big angle. 135 makes sense for what we see on the page. The interior angles of regular polygons on the next one. 21 has 1, 2, 3, 4, 5, 6 angles. It's a hexagon. So if we refer back to the other one, we can see that's going to be 120 degrees for each one. On number 22, that's 1, 2, 3, 4, 5, 6, 7. That's a heptagon or septagon. It's 128.571, so precise. And then number 23, that's a triangle. Each one of those is 60. On the last one there, it says find the value of x. Remember, our exterior angles are going to add up to 360. So again, I'm just typing this into Desmos. 360 minus, I'm going to start with the the 76 and work my way around. So I'm going to subtract 76, then I'm going to subtract 54, then I will subtract 75, subtract 44, subtract 65. What I have left is 46, which makes sense for what I see there. That X degree angle there is a 46 degree angle. And then on the last one, again, doesn't matter how many sides, they're going to add up on those exterior angles to 360. So I take my 360 and I'm going to subtract 71, subtract 85, subtract 44. That's going to give me 160, and I have 3x and 2x. So I'm going to take that 160, and when I put 3 and 2 together, I get 5. I'm going to divide that. Would help if I hit divide instead of subtract. Divide that by 5. That's going to give me 32 for each x, meaning that I have a 96 degree angle where that 3x is and a 64 degree angle where the 2x is. Hopefully this helps you out. If you have questions, you can save them for when I come back on Monday. Good luck.